Hi everyone, welcome back to the class. In today's class, we'll be learning about recursion. In C, it is possible for the functions to call themselves. A function is called recursive if a statement within the body of a function calls the same function. Sometimes called circular definition, recursion is thus the process of defining something in terms of itself. Let us now see a simple example of recursion. Suppose we want to calculate the factorial value of an integer. As we know, the factorial of a number is the product of all the integers between 1 and that number. For example, 4 factorial is 4 into 3 into 2 into 1. This can also be expressed as 4 with exclamatory mark, which is equal to 4 into 3 exclamatory, where exclamatory stands for factorial. Thus, factorial of a number can be expressed in the form of itself. Hence, this can be programmed using recursion. However, before we try to write a recursive function for calculating factorial, let us take a look at the non-recursive function for calculating the factorial value of an integer. And the output for this program would be, so please work through this program carefully till you understand the logic of the program properly. Recursive factorial function can be understood only if you're thorough with this particular program. Following is the recursive version of the function to calculate the factorial value. And the output of this particular program would be, let us understand this recursive factorial function thoroughly. In the first run, when the number entered through scanf is 1, let us see what action does REC take. The value of a, that is 1, is copied into x. Since x turns out to be 1, the condition if x is equal to 1 is satisfied, and hence 1, which indeed is the value of 1 factorial, is returned through the return statement. When the number entered through scanf is 2, then x is equal to 1 test fails. So we reach the statement f is equal to x into REC of x minus 1. And here is where we meet recursion. How do we exactly handle the expression x into rec of x minus 1? We multiply x by rec of x minus 1. Since the current value of x is 2, it is same as saying that we must calculate the value 2 into rec of 1. We know that the value returned by rec of 1 is 1. So the expression reduces to 2 into 1, or simply 2. Thus the statement x into rec of x minus 1 evaluates to 2, which is stored in the variable f and is returned to the main, where it is duly printed as factorial value is equal to 2. Now perhaps you can see what would happen if the value of a is 3, 4 and 5 and so on. In case the value of a is 5, main would call rec with 5 as its actual argument, and rec will send back the computed value. But before sending the computed value, rec calls rec and waits for a value to be returned. It is possible for the rec that has just been called to call yet another rec, the argument x being decreased in value by 1 for each of these recursive calls. We speak of the series of calls of rec as being different invocations of rec. These successive invocations of the same function are possible because the C compiler keeps track of which invocation calls which. These recursive invocations end finally when the last invocation gets an argument value of 1, which the preceding invocation of rec uses to calculate its own f value, and so on up to the ladder. So we might say what happens is, so rec gets a value of 5, which then multiplies 5 into rec of 4, which then returns and gets the value of 4, and then gets multiplied with 4 into rec of 3, and this process continues till we return a value of 1. Foxed? Well, that is recursion for you in its simplest guise. I hope you agree that it's difficult to visualize how to control flows from one function call to another. Possibly, this particular figure would make things a bit clearer. Assume that the number entered through scanf is 3. Using this figure, let's visualize what exactly happens when the recursive function rec gets called. Go through the figure carefully. The first time when rec is called from main, x collects 3. From here, since x is not equal to 1, the if block is skipped and the rec is called again with the argument x minus 1, that is 2. So this is a recursive call. Since x is still not equal to 1, rec is called yet another time with argument 2 minus 1. This time, as x is equal to 1, control goes back to the previous rec with the value 1 and f is evaluated as 2. Similarly, each rec evaluates its f from the returned value and finally 6 is returned to the main. The sequence would be grasped better by following the arrows shown in the figure. Let it be clear that while executing the program, there do not exist so many copies of the function rec. These have been shown in the figure just to help you to keep track of how the control flows during successive recursive calls. For you, recursion may seem strange and complicated at first glance, but it is often the most direct way to code an algorithm, and once you are familiar with recursion, the clearest way of doing so. Next, going to recursion in stack. There are different ways in which data can be organized. For example, if you are to store 5 numbers, then we can store them in 5 different variables, an array, a linked list, or a binary tree. All these different ways of organizing the data are known as data structures. The compiler uses one such data structure called stack for implementing normal as well as recursive function calls. A stack is a last in first out, that is LIFO data structure. This means that the last item to get stored on the stack, often called as push operation, is the first one to get out of it, often called as pop operation. You can compare this to the stack of plates in cafeteria. The last plate that goes onto the stack is the first one to get out of it. Now let us see how the stack works in case of the following program. In this program, before transferring the execution control to the function fun, the values of parameters a and b are pushed onto the stack. Following this, the address of the statement printf is pushed onto the stack and the control is transferred to fun. It is necessary to push this address on the stack. In fun, the values of a and b that were pushed on the stack are referred as I and j. In fun, the local variable sum gets pushed on to the stack. When the value of sum is returned, sum is popped up from the stack. Next, the address of the statement where the control should be returned is popped up from the stack. Using this address, the control returns to the printf statement in main. Before execution of printf begins, the 2 integers that were earlier pushed on the stack are now popped off. How the values are being pushed and popped even though we didn't write any code to do so? Simple. The compiler, on encountering the function call, would generate code to push parameters in the address. Similarly, it would generate code to clear the stack when the control returns back from the fun. This next figure shows the contents of the stack at different stages of execution. Note that in this program, popping of sum and address is done by fun, whereas popping of the 2 integers is done by main. When it is done in this way, it is called as cdecl calling convention. There are other calling conventions as well, where instead of main, fun itself clears the 2 integers. The calling convention also decides whether the parameters being passed to the function are pushed onto the stack in left to right or right to left order. The standard calling convention always uses the right to left order. Thus, during the call to fun, firstly, value of b is pushed to the stack, followed by the value of a. The recursive calls are no different. Whenever we make a recursive call, the parameters and the return address gets pushed onto the stack. The stack gets unwounded when the control returns from the called function. Thus, during every recursive function call, we are working with a fresh set of parameters. Also, note that while writing recursive functions, you must have an if statement somewhere in the recursive function to force the function to return without recursive call being executed. If you don't do this and you call the function, you will fall in the indefinite loop and the stack will keep on getting filled with parameters and the return address each time there is a call. Soon the stack would become full and you will get a runtime error indicating that the stack has become full. This is a very common error while writing recursive functions. So basically my advice is to use printf statement liberally during the development of recursive function so that you can watch what is going on and you can abort execution if you see that you have made a mistake. Next, going to adding function to a library. Most of the times we either use the function present in the standard library or we define our own functions and use them. Can we not add our functions to the standard library? And would it make any sense in doing so? We can add user-defined functions to the library. It makes sense in doing so as the functions that are to be added in the library are first compiled and then added. When we use these functions by calling them, we save on their compilation time as they are available in the library in the compiled form. Let us now see how to add user-defined functions to the library. Different compilers provide different utilities to add or delete or modify functions in the standard library. For example, Turbo C or C++ compilers provide a utility called tlib.exe, that is Turbo Librarian. Let us use this utility to add a function factorial to the library. Given below are the steps. The first step would be to write the function definition of factorial in some file, say fact.c. So this would be the program which you would be using to define a function factorial. The next step would be to compile the fact.c file using Alt F9. A new file called fact.obj would get created containing the compiled code in machine language. The next step is to add the function to the library by using the command. Here, math.lib is a library file name, plus is a switch, which means we want to add a new function to the library, and c:/fact.obj is the path of the obj file. The next step is to declare the prototype of the factorial function in the header file, say fact.h. This file should be included while calling the function. The next step is to use the function present inside the library, so create a program as shown here. And the final step would be to compile and execute the program using Ctrl F9. If we wish, we can delete the existing functions present in the library using the minus switch. Instead of modifying the existing libraries, we can create our own libraries. Let's see how to do this. Let us assume that we wish to create a library containing the functions factorial, prime, and Fibonacci. As their name suggests, factorial calculates and returns the factorial value of the integer passed to it. Prime reports whether the number passed to it is a prime number or not. And Fibonacci prints the first n terms of the Fibonacci series, where n is the number passed to it. With that, we have come to the end of our class. And let's just summarize what we have learned today. To avoid repetition of code and bulky programs, functionally related statements are isolated into a function. Function declaration specifies what is the return type of the function and the types of parameters it accepts. Function definition defines the body of the function. Variables declared in a function are not available to other functions in a program, so there won't be any clash even if we give same name to the variables declared in different functions. Pointers are variables which hold addresses of other variables. A function can be called either by value or by reference. Pointers can be used to make a function return more than one value simultaneously. Recursion is difficult to understand, but in some cases offer a better solution than loops. Adding too many functions and calling them frequently may slow down the program execution. So with that, we have come to the end of our class. In the next class, we'll discuss about the data types revisited. Thank you.